first look at what is RabbitMQ and Kafka. So both of these are essentially data transmission frameworks. Okay, Kafka or Apache Kafka. It was started at LinkedIn, and RabbitMQ is founded as well as maintained by Pivotal. Pivotal is the company behind Spring. So both of these have pretty much strong industry backing. I have used both of these frameworks, and it's fairly interesting, and that's why I decided to put this talk together. So with that said, let's look at some basic concepts of Kafka. So Kafka is nothing but a transaction log. Okay, and as you know, and when I say transaction log, that means a database transaction log. So the golden source of truth is essentially in the log. Okay, and similar to a database transaction log, if anytime you want to look at what exactly happened, what's the data, etc., you can look at the log. You can replay the logs in order to restore the data, restore the place of the configuration or the data in the database, so on and so forth. So with Kafka, borrows the exact same concept of a transaction log. Secondly is Kafka relies on Zookeeper. So far, and Zookeeper is responsible for maintaining the configurations. Okay, and configurations as well as the topology. So essentially, Kafka relies on Zookeeper to sort of keep a tab on which all are the Kafka brokers, how many topics are there, who is the producer, how many consumers are there, and the consumer groups. So I literally covered a few concepts out there. Let me note them down. So broker or server. So in Kafka terminology, a Kafka server is essentially called as a Kafka broker. This is where messages are stored when pushed by a producer to a topic. Now the next concept, everyone will be like, hey Nikhil, what is topic? So topic is essentially the subdivision or classification of messages. Again, the way we define the topic or the way we define the classification is completely up to us. But what Kafka gives you is the ability of bifurcating the messages according to sort of a business use case. A simple use case would be like, let's say, a ticket booking system where at the end of the day you're trying to book a ticket, but let's say you're trying to book a bus ticket, a train ticket, an airplane ticket, a ship, a boat or a ship ticket, right? So all of these are essentially book tickets only, but what you're trying to do is you're trying to have them separated by sort of a business use case. So that's where topic comes into picture. The next one is producer. Producer is some it's a process which actually produces the messages. And then lastly, the consumer is a process which consumes the messages. So that was for Kafka. Now, similarly for RabbitMQ, we also have some basic concepts of RabbitMQ. The most important thing to realize is, as the name says, MQ. So it is a queue. Okay, it is a queue, but it is not just any queue. It is a smart queue. Okay, and the smartness of the queue is actually dictated by an element of the entire infrastructure, which is called as exchange. Okay, before we go in exchange, let's take a step back and understand that RabbitMQ actually relies on Erlang. It's a language which you'll have to install if you don't have it. It comes with its own server. And this server is essentially responsible to keep the configuration, and this is responsible. The server is responsible to retain the configuration. So essentially, who is the producer, who is the consumer, how many queues are there, what is the exchange, and everything. Going back to, I'm just going to copy exchange over here. So exchange is where this is the smart component of the system. So or rather, I would say this is the primary reason why RabbitMQ, becomes smart, because one of the things which you have to realize about RabbitMQ is it has a publisher and a subscriber model, which can be fairly trivial. However, the exchange is where all the the fun is, where you can have the routing rules, etc., etc. So the routing rules, then routing types, as well as queues. So essentially, an exchange gives the messages to queues. So the queues are connected. Queues connect to the exchange and deliver messages. Uh, Second to last is producer. Producer is a process which produces the messages and pushes them to exchange. Okay, and that's always the first step. But whenever you're pushing it to a particular queue, you're indirectly pushing it to an exchange, and the exchange makes it available on the queue. And then lastly, it's the consumer. And in case of RabbitMQ, a consumer is what consumes the message. A message consumes the messages from the queue. Okay, so there's a bit of a difference. So basically, a producer produces a message, it is sent to the exchange. Exchange decides what exactly needs to happen with the message, and then which queue it needs to route to, and then puts it on that queue, and a consumer picks it up from that queue. Okay, so one of the important things that you need to realize is the biggest difference between Kafka and RabbitMQ is that in RabbitMQ, the moment you have actually read the moment a consumer has actually read a message from the queue, the message is lost. It is and when the consumer has acknowledged that the consumer has actually produced the message, the message is lost. You don't have the ability to sort of get the message back on the queue. Compared to that, in Kafka, because everything is a transaction log, while the logs are retained, you can always replay the messages. Now let's actually look at this in a simple demo. So let's look at MQ, simple producer and consumer. Essentially, as you can see, we end up creating a new connection. And as I mentioned before, for MQ, the moment you start up the server basically takes care of everything. It takes care of creating your exchange. It takes care of creating your queues, etc., etc. That said, if let's say a queue is not present, and when you're trying to run your program, because you're doing a queue.declare, if a queue is not present, then MQ is smart enough to actually create that specific queue. There are a few parameters, and it is completely configurable. When you say durable, that means if your MQ server actually goes down, then what should happen to the messages? Since it's for demo, we don't really care, so that's why durable is false, where you essentially mean that hey, if the server dies, then all the messages are lost, and you just have to recreate the messages again. Okay, and it's a simple program where we are just having a for loop which goes from 0 to 4, and it's going to just basically publish it to the simple queue. And if you see here, this is the exchange, and I've put a blank exchange, and that's pretty much the default exchange. Later on in the examples, we'll see another named exchange when we are looking at pub/sub mode, and we'll see what happens. The other aspect of this is the MQ simple consumer, and if you look at the MQ simple consumer, it's pretty much the converse of the producer, where we are declaring similarly the queue, but instead of publishing, you're consuming. And here there's a configuration called as auto ACK. That means that the moment the message hits the consumer, MQ does not wait for consumer to say that, hey, I'm done processing. It does not wait for it to acknowledge that I'm done processing. It just says true and moves on. So and all we're doing is we're taking the message and logging it. So let's actually see a few of the differences. So let's start the producer first, and I'm starting it first for a particular reason, and you'll see why. So we started 0 to 4, and the producer stopped. Now let's actually start the consumer. And if you see, the consumer was started, it is already in a loop, in pretty much an infinite loop till we actually kill it. It consumed the messages that were put on the queue. Now, here's the interesting thing. If I end up starting this again, then it will end up consuming the messages again. But now, if I need to, let's say, start consuming the messages from like literally the start, this was the very first message that the consumer got. I do not have any way to sort of replay the message. Okay. Now that was MQ. So let's do a quick recap on what we saw in MQ. So in MQ we saw the producer, the consumer. We also saw the simple configuration in Java, and we discussed about not being able not being able to replay the messages. Okay, so now let's look at how it works with Kafka. So Kafka simple producer is again similar to sorry, this is MQ. We are looking at Kafka simple producer, sorry. So again, similar to MQ, Kafka is also pretty configurable, where you're essentially saying that like I have properties, these are my bootstrap servers, and before the talk started, I actually brought up my Zookeeper instance. So this is my Zookeeper instance, and this is my broker or my Kafka server, which is running on 9090. So let's actually that's what I'm going to connect to. Then I'm going to end up pushing my keys and my values as just string, because that's a string serializer. And over here I'm going to publish messages from 1 through 20. And after I have created the producer, I'm going to end up pushing it to a simple topic with a key and value. The keys and values have some interesting meaning and interesting reasons behind it. For the interest of time, we will not go through them, but we will actually see them in practice in some of the next demos. So let me go ahead and start the producer. And similar to MQ, because I did not have a topic previously created, this Java client is actually smart enough for Kafka, where it will go and provision a topic on this server. Generally, in an industry setting, you don't let this default just take place. Like for neither for MQ nor for Kafka, you will end up creating your queues as well as your topics beforehand. So that was the producer, where I went. Let me actually stop MQ just so that we have less noise out here. If you see here, the producer started. It ended up connecting, and then it ended up publishing the message. Now let's go ahead and look at the consumer. So similar to the MQ consumer, that's the same thing that happens, where we are saying that, hey, I'm going to connect to 9090. That's where my server is. And since my producer was serializing it as a string serializer, I'm going to deserialize it using the string deserializer, so I can get the message. Then you have some of the properties over here. This is the group ID, and Kafka relies on consumer groups, where essentially consumer group is sort of the way in which you can separate one or more consumers. So if you have a different consumer group, then Kafka knows that, like, hey, this particular consumer group has not gotten any messages, then it will be able to send those messages out. And we'll see that in practice in a second. The enable auto commit, that this is similar to the ACK that we had seen in MQ, where we are basically saying that, like, hey, I do not want you to auto commit. This is false. I want to manually acknowledge. So if you see here commit sync, I manually want to acknowledge that I have consumed a message. Then last but not the least, these are the consumer records, and we keep on sort of going through them and reading them. So let's actually run this and see how the consumer behaves. So if you see here, again, we ended up consuming all the messages from 1 through 19. Now if we go back to the producer and start the producer, and we know the producer produces messages, but over here you will see on the consumer side as well, it will start consuming the messages one by one. after the producer ends up producing messages. So if you see here, we already produced the messages. This was the first batch from 1 through 19. Then this is the second batch. Now, if you remember, while we were looking at MQ, I said, if let's say I want to replay all the messages from the start, in MQ I don't have a way, because once the messages are essentially consumed, they are gone from the queue. Kafka does, because of the way in which Kafka is designed, it gives you the ability to sort of replay the messages from a particular point, and that is done by the concept of an offset. So in Kafka terminology, an offset is essentially your unique ID on your topic and partition for a particular message. So you can always, as long as a particular message still exists in the logs, because Kafka has the retention period plus, depending on your log resources and everything, your file resources, if as long as the message is there, you have the ability to seek your Kafka consumer to a particular place. And let's actually see that in real practice. So what I'm going to do is, I've already done the Kafka consumer here. So I'm going to say Kafka consumer dot get assignment. So essentially, this assignment will tell me that what exactly is assigned to my, what exactly this Kafka consumer is assigned to. Now, interestingly, whenever the process starts, it takes like a little bit of time for Zookeeper to understand that, like, hey, I have a process which is trying to read from this topic. It also takes a second for it to understand from where it is trying to read, what is the consumer group, etc., etc. Right? What we have to do is we have to always check whether a particular topic is assigned or not. So what we are going to do is we're going to check whether the assignment is empty. If it is empty, then our favorite thread.sleep, we're going to sleep for a second. Okay, and after that, we are going to say Kafka consumer.poll. And we are going to just poll for with a timeout of 10 milliseconds, and then we are going to check the assignment again. So we are basically going to say Kafka assignment.assignment, and exactly what we did. So the moment the assignment turns to be non-empty, it will actually return it. And because we like to know what is going on, let's actually log the assignment, what is going on, right? Assigned to, okay. So with that, we will know what exactly we are assigned to. Now that we know that we are assigned to a particular topic, and because I set up the demo, I know that we'll be assigned to this topic, which has only one partition, and by default, the partition number starts from 0. It's 0 index. And let's say we want to move our reading to some, like, I mean, let's just make it easy, to the beginning of this particular topic. So what you have the ability to do is you have the ability to say seek to the beginning, right? And you can say Kafka consumer.seek to beginning, and it needs basically a collection of topic partition. And a topic partition is nothing but it takes in a topic, and in this case, the topic name that we have subscribed to is simple topic. So we can just use that. So topic type dot simple topic dot get name, and we will be resetting partition number 0. So there you go. Once we have seek to the beginning, then we'll see what exactly happens. And if you see here, this Kafka simple consumer is still running. My producer is not running. So nothing new is getting consumed. And so essentially, I can just restart, and then we'll see this code in action. After this is done, you will see that just because the way Kafka is designed, where it is set up as a transaction log, we are actually able to go back, rewind, and replay all the messages. So if we look at the logs out here, we actually know that, like, hey, it is assigned to simple 0, and we are resetting the offset to offset 0. Okay, so this was one way in which you could replay the message. Okay, but let's say a completely new consumer comes to you and says that, like, hey, you're sending this data to consumer 1. I want that exact same data as well. Now, if it was the case of MQ, the data is gone. So you basically can say that, like, hey, whatever data will produce in the future, you can get it by using the pub/sub model. But in case of Kafka, what you can do is, I'm just going to delete this part because we don't care about assigning anymore. or I can just comment it out. And basically, that's where Kafka's beauty comes in place, where you have this concept of group IDs or consumer groups. And in this case, what happens is if there's a new consumer, you can just change the consumer group, okay? And then what Kafka will do is Zookeeper will understand that, hey, this is a new consumer group, and what we have set up here is auto offset reset to be earliest. So basically what we are telling Zookeeper is that, hey, if you do not have an offset, if you do not have the last consumed message available in your system, then basically give me the earliest message that is there. So right now, just because I changed it to test group 2, we actually got all the messages from the start. Okay, we had produced the same set of messages twice, and you can see we got the same messages. Now let's say the third consumer comes, we can do the exact same thing. We get the third consumer, and we get it to play. So with that, this was a fairly simple demo. So let's quickly recap what we did for Kafka. So we saw the producer, similar to MQ, producer, consumer, and the simple configuration in Java. We discussed and demonstrated the the feature slash capability of Kafka to replay a set of messages. We also demonstrated the pub sub model, which is by default Kafka's model, pub sub model, where a mess the same message can be consumed by multiple consumers from the broker. Okay. So with that, I'm going to move to the next cool aspect called as scaling. Now, why scaling comes into picture in this big data world is due to multiple reasons. One, we are dealing with tons and tons of data, like a lot of data. So now imagine you have a process which takes which produces 1 million messages, and let's say you have a consumer, which you have another process which ends up processing these 1 million messages, but it takes 1 second for every single message to be processed. So what I mean, simple math, what's going to happen is it's going to take you 1 million seconds to essentially consume all the messages. Now, the best answer to that is, okay, we need things to be faster. We can't spend 1 million messages. So people will say, okay, fine, multi-threaded, okay? But there's only so much of parallelism you can do because of your system, like how much your core can actually give, how many threads you can give. Let's say your thread, your machine can only give spare 10 threads because of some reason or the other, some limitations. So essentially, instead of now 1 million seconds, it's going to take you 100,000 seconds. But let's say someone says that hey, I want you to produce, I want you to process all 1 million messages in one go. So essentially, what you need is you need 1 million threads to produce. To process all the messages. Now that creates a very interesting problem, because essentially for you to get 1 million threads at the exact same time to process all the messages, you essentially need pretty much a supercomputer. Okay, so that's where the whole concept of distributed programming came, where what you can do is it's more expensive to get one big machine, but it's fairly cheaper to get small machines. And if you have multiple small machines together, they can actually form sort of a unit, like an army of processors. And let's say if one of the processor actually one of the small systems actually goes away, it has an issue or something like that, you can always replace it fairly inexpensively with another equally small system. This also gives you better resiliency and better bang for the buck. So that's why scaling is important. Now, the way Kafka and RabbitMQ does scaling is fairly interesting. So let's look at RabbitMQ first. So MQ scaling producer, and essentially this producer is the same thing, but instead of like producing 5 messages, now in this case I'm going to produce 20 messages, 1 through 20. So let's go ahead and produce them. And while it is producing, what I'm going to do is I'm going to have one consumer just come up, and let's see what happens. So one consumer is consuming one message for every per half second, okay, because that's the complexity that I've given. So it takes half a second for every message to be consumed by this consumer. Now someone says that like, hey, that's not enough for me. You need to process messages in a faster way, and there are some messages which might even take like 1 second. So let's actually go to essentially another consumer, and in this case this consumer is going to take 2 seconds to consume one message, and let's start it. And before I start it, this is what I'm going to do. I'm going to produce messages again, and at that time I'm going to start the consumer. So and you will see why I'm doing this in a second. So as you can see, consumer 1 is still processing messages, and we have started consumer 2, but consumer 2 did not get any messages yet. Okay, consumer 2 has started, however it did not get any messages yet, and that is mostly because of a property that we have to set in MQ, and the property is for prefetch. So similar to the max number of records that we set in Kafka, in here as well we have the prefetch limit, where you're basically saying that like, hey, only give me one message at a time. Like previously what had happened was we had 2 consumers, but because consumer 2 was not seen by the by MQ while it was pushing messages to consumer 1, it said that like, hey, I don't have any consumer, I only have one consumer, so I'll push everything. Now let's see the exact same difference, what will happen when we end up putting count as 1. So and I'll replicate this exact same experiment. So I'll first bring down both of these, okay, and then I'll only bring up consumer 1. Okay, and once I have brought up consumer 1, I'm not going to bring up consumer 2 yet. I'm going to actually start the producer to produce the messages, and as it has produced the messages, you can see that consumer 1 is consuming the messages. Let me quickly go ahead and start this consumer 2. And as you can see, it picked up message number 13, then 16, then 19, and it ended up consuming 3 messages, and consumer 1 consumed 17 messages. Okay, so that way, we were able to quickly scale. And the reason why we had not scaled before is because of the prefetch limit. I wanted to show that that very important configuration, because sometimes you might think that like, hey, why is I got a new consumer, but it's not getting anything else. Now someone comes and says that like, hey, just 2 consumers are not enough. I want I want you to consume things in a much faster way. Okay, now just for this example, what I'm going to do is, instead of taking half a second, I'm going to actually bump up both of these to consume a message every 5 seconds, just so that you can see the impact when we end up bringing the third consumer on. So and that's sort of fairly important. I'm not bringing up the third consumer yet. I'm just going to start the producer. The producer will produce the same 20 messages again. Oops, sorry, wrong producer. So I'm looking at the scaling producer. Sorry. Yeah, let us start the scaling producer again. It will end up producing 20 messages. As you can see, these guys are consuming slowly. Let's actually go ahead and start a third consumer, and the third consumer is essentially super fast. It takes just 10 milliseconds, okay, to consume a message. So let's see it come up. And if you see, now it joined the cluster and it consumed 12 messages. It came from behind and it said that like, hey, give me a message, I'm done. Give me a message, I'm done. And so we successfully scaled the system. And now if you can see, consumer 1 consumed only 3 messages, consumer 2 consumed 5 messages, and consumer 3 consumed 12 messages. So essentially all 20 were consumed, but we were able to scale our system by just adding more and more and more consumers on the same queue, because they would just pick it up. Okay, this is a very important property of MQ, where you can just go on scaling horizontally by adding more consumers. Now let's see what happens with Kafka. I'm just going to go ahead and close everything else, and let's just do Kafka scaling producer. So similar to that, similar to our MQ, we are publishing the exact same messages to our topic. So let's just go ahead and produce them. So we got these 20, and now similar to MQ, I also have 3 consumers out here, and I'm fetching just one record at a time. So let me go ahead and start consumer 1. Okay, it will go on consuming. Let me go ahead and let it finish. It will take another like a couple of seconds, and once that is done, let me start consumer 2. Okay, I'm not going to start consumer. Oh, why not? We'll just start consumer 3. So because I would like to show everybody like the the things that happen when you start multiple consumers. Now remember, I was mentioning about partitions in a topic. So partitions is Kafka's way of enabling parallelism. So anytime you have a topic, if you have a partition, then only one consumer can consume from that partition. So if you see here, I've started consumer 3. Look at the logs. It does not have any partitions assigned to it. I started consumer 2. It says it has topic 0, partition number 0 assigned to it. And if we look at consumer 1, it does not have any, what do you say, any partitions assigned to it. Okay, so now that said, the interesting thing is when I start my producer, we will see the impact of that. So we produce the message, but now you will see that I have 3 consumers, but only one consumer is consuming the messages. That is consumer number 2, because that's the only consumer which is attached to essentially a particular partition. Because the rule in Kafka is that every single every partition can have only one consumer, and the reason for that is because Kafka guarantees ordering in a particular partition. The moment you have more than one consumer, then the guarantee for ordering will be lost, because let's say one consumer is able to consume faster than the other consumer, then it causes the synchronization issues and everything. So that's the reason why in Kafka, if you only one consumer can consume from one partition. So the way you can add scaling or parallelism to your process in Kafka is by actually adding partitions. So normally, if such a thing happens, then you basically tell your Kafka team to go and alter your topic and actually increase the partitions. In this case, I'm only going to increase it to 3. Okay. Now, one of the interesting things that while Kafka is altering the partitions, it's worth mentioning is that the moment you alter the partition, Kafka does not go and rebalance your consumers. It does not go and tell that like, hey, I have 3 consumers and I have 3 partitions. Okay, I'm going to end up reallocating the partitions like after you have altered the number of partitions. But let's say you already had partitions present and then you add more consumers, then Kafka will then Zookeeper will rebalance it. So let me show that in real life example. So let's first like bring down all the consumers. Okay, our producer is already down. So and we have brought down all the 3 consumers. Let's actually start a particular consumer. What will happen is it will say I'm rejoining the group, etc., etc., and you will see that consumer 1 is now assigned to topic 1, partition number 1, partition number 0, and partition number 2. Okay, we will go ahead and start consumer number 2. Okay, and that one is now it will end up rebalancing and everything, and now it says that hey, this is attached to partition 1 and partition 0, and it would have rebalanced this consumer number 1, and it says that hey, I am attached to just partition number 2. Okay, we won't bring up consumer number 3 yet. Similar to what we had done with MQ, we're just going to increase the amount of time that these take to actually consume the messages. So let's actually bump it up to 55,000 milliseconds, so 55 seconds, and let's stop and rerun this, and we can stop and rerun this, and we are not bringing up consumer 3 yet. Okay, so remember that we are not bringing up consumer 3 yet. We are going to go ahead and publish all the messages. It has published from 1 through 19, and you will see that consumer 1 is consuming messages from partition number 2, consumer 2 is consuming message from partition 0 and 1, and now let's say consumer 3 comes into picture. What Kafka will do is that time Zookeeper will dynamically rebalance the system and say that, like, hey, I have 3 partitions, I have 3 consumers, so each of you get one partition. And now if you will see, this consumer number 2 is actually now only pulling from partition number 0. Consumer number 1 is pulling from partition number 1, and consumer number 3 is pulling from partition number 2. So if you'll see 0, 1, and 2, either that happened or yeah, max pull records of 1. So let's go ahead and actually rerun this and see what exactly happened. So there you go. This started consuming from partition number 2, and this would be consuming from partition number 0 as before, and previously this similar to before, this is consuming from partition number 1. So that way you have the ability to dynamically scale your particular sort of partition, your system, and that's by the virtue of partitioning. So let's stop all of these 3 and do a quick recap of how scaling happens. So as we had seen in MQ, if you want to scale, just add more consumers, and depending on the rules, MQ will start pushing out messages to the new consumers. Okay, in Kafka, the scaling is a little bit intrusive, where if you want to scale more, if you want to scale more for consumers, then you need to add more partitions to the topic. Okay, and the reason for that is one partition can have only one consumer consuming from the topic. Okay, however, one consumer can consume from multiple multiple topics, sorry, multiple partitions in a topic. I mean, of course, one consumer can consume from multiple topics as well, but that's a different story. But we are looking at only partitions right now. Lastly, the reason why one partition can have only one consumer is because Kafka guarantees ordering, okay, for messages within a partition. So what I'm trying to say is, if you have messages 1, 2, 3, 4, 5 in a particular partition, then that order is guaranteed by the virtue of offsets and logs. And essentially what I'm trying to say is, like in Kafka, because Kafka is a transaction log, the order of your logs is always retained. So what ends up happening is, if you have a message which has to go from 0, 1, 2, 3, 4, 5, that ordering is guaranteed within a particular partition. But in case of MQ, because of scaling, the way the consumption will actually happen, there is no guarantee of ordering. Okay, because essentially, as we saw, consumer 1, 2, 3 were consuming at their own rates. It's possible that, like, suddenly one consumer will drain all the messages. But in that case, what's going to happen is, let's say message number 3 gets processed before message number 1, or message number 10 gets processed before message number 3 is processed. So so on and so forth. Again, this is sort of fairly important. So looking at what I had mentioned, and just summarizing it in terms of ordering, Kafka guarantees ordering for for messages within a partition. Okay, in MQ, ordering is not essentially 100% guaranteed, and that is mainly due to multiple reasons. It can be due to consumption rate. It can be due to exception handling. Okay, which leads me to the next part of the talk, which is the exception handling. We are going to look at RabbitMQ first, as always, MQ exception handling. And in this case, we are basically, again, creating these messages from 1 to 21. And in case of the consumers, what we are saying is that consumer number 1, if a particular message is even, it does not want to process them, and consumer number 2 does not want to process any of the odd messages. So in MQ, you have the ability of essentially requeuing a message on failure. So let's say this is a try catch, and you have you reject you reject a particular message for some reason. So you're basically saying you want to either requeue it or you don't want to requeue it. In this case, we want to requeue it. So let's actually requeue it to true. And when you don't requeue it, when you requeue it as false and you reject a message, what MQ does is it puts it in a dead letter queue. So exception handling is pretty much supported out of the box by MQ, where it will put it in a dead letter queue, and by adding a little bit more configuration, you can actually configure the dead letter queue and a little bit of more code to actually push it back to the back of the queue. Let's see it in practice. I'm going to bring up consumer 1 first, which does not want to consume even messages, and then I'll end up bringing up consumer number 2. Okay. And I'm just bringing them up in that order because it becomes easier to navigate over here. So we got consumer 1, we got consumer 2, and then we'll go ahead and start the producer. Now you will see an interesting thing, right? Over here, consumer 1 got message 4, and it keeps on rejecting that it does not want to process even messages. Consumer 2 got message number 5, and it says it now does not want to process odd messages. Now, this is where, going back to the whole ordering example, that ordering sort of property that I was trying to explain before, right? Now, in this case, if let's say consumer 2 just goes away altogether, what will happen is consumer 1 is trying to consume message number 4. Okay, let's say we bring down consumer 1 as well. Okay, by default, whenever you reject a message, MQ puts the message at the top of the queue. Okay, so if I end up restarting, or more than top of the queue, it ends up putting the message back to where exactly it picked it up from. So that's why we are picking up message number 4 to begin with. So what I'll do is I'll stop this, and I can just start consumer number 2. So we can keep on playing this ping pong over and over again. But now in this case, it consumed message number 5, and now we are back to odd. So what we are saying is we can start consumer number 1, and then that will take message number 6, and this process will go on literally forever. So essentially, because the ordering is not guaranteed in which consumer 1 and 2 will get these messages, you don't really know which consumer will actually react to what first. So you have a few options to deal with exception handling. The very first option is you basically say, no, I don't want you to requeue. I just want to go to false. So what false is going to do is it's basically just going to reject the messages which failed. So let's go ahead and start consumer 1 and 2 again. So it started consumer 2. Let's start consumer 1. And you will see here it's processing messages. It got 9, it got 12, but this guy got 13, this guy got 14, 16, 17, 19, so on and so forth, right? But it does not want to process even messages. So here what we are saying is message number 20 will not have come over here. This the consumer 2 has stopped consuming messages because we said we don't want to requeue. Now, essentially, when you say you don't want to requeue, what happens is behind the scenes, MQ actually puts this in a dead letter queue, which you can use later on. But more than that, the other interesting thing that you can do is, instead of rejecting it, you basically say that like, hey, I understand you sent me this message, it is incorrect, but I'm going to say, okay, I see you. I'm going to put you back in the queue. This is similar to like, if you stand in a ticket line, let's say at a movie theater or something like that, and over there, like, let's say one ticket line is for movie 1, the other ticket line is for movie 2. There, it ends up happening that like someone says that, hey, I want tickets for movie 2, but the person says, sorry boss, this is only for movie 1. Then at that time the person has to go back and stand back in the queue, and then they decide which window they get to. So that's exactly what pretty much we are doing. So let's actually go ahead and start consumer 1 and consumer 2 again. And this, according to me, is fairly interesting because we will see how we have to do the same thing in Kafka in a minute. We started both the consumers. Now let's actually start the producer so that we can produce the messages again. And oops, I meant to start the producer. Okay, so we'll produce the messages, and if you see, consumer 1 is getting 1, 2, 3, 4. It got 6, 7, 9, etc., etc. But what it is essentially doing is now it's requeuing at the back of the queue. Okay, so if you see here, this consumer number 2 got the messages which essentially consumer number 1 was actually rejecting, and vice versa. Now this is where like the ordering sort of cannot be guaranteed, because now we are basically playing a game of chance where consumer number 1 got message number 6 like 3 times, and it went on rejecting until consumer number 2 got message number 6 and actually consumed it and acknowledged it. Okay, so that's sort of the interesting thing where you can just requeue it, and then you can have like your consumers pick it. But MQ allows, in the interest of time, we'll most likely won't be able to cover that, but MQ allows very smart routing, but I will try to cover it in a minute. Let's go to the exception handling of Kafka. So the Kafka exception handling is, I would say, a little bit cumbersome. And the reason why I call it's cumbersome is because the producer can go on producing messages. Okay, because Kafka is essentially a transaction log, there is no way for you to essentially skip a message. Even in this case, let's say you don't want to process even messages, you do not have the option of just skipping a message and picking the message later on. What you essentially have to do is you have to essentially acknowledge the message. Okay, you have to say that like, okay, fine, I see the message, and if there is a failure, then you basically say that like, hey, push it to another topic, and I call it like the exception topic, which we can have another consumer consuming from it. So let's see how this actually works. So we got consumer 1 who is only going to consume from topic 1. So who is only going to consume the even messages, and as you can see over here, it just kept it kept on consuming the messages from sort of 2, 4, 5, 6, 7, 8, 9, and it threw the exception, but it kept on moving ahead. And the reason why it kept on moving ahead is because we were acknowledging it. Now let's actually start consumer number 2. It will do the same thing where it will consume, it will throw an exception, and it will push it onto another queue, which we another topic which we called as an exception processing topic. Now essentially we can then have like a super duper consumer which is consuming from this exceptions topic, which says that, hey, give me any message that you can, and I will be sure to consume it. And that's what's happening. So now technically consumer 1, we started consumer 1 first, and then we started consumer 2. So consumer one would have rejected all the even messages. So in our exception topic, all the even messages would come first, and then after that, all the odd messages will come. So let's see how it is happening. So if you see here, all the even messages are being processed before, and after that, all the odd messages are being processed after that. So essentially, what Kafka is saying is, hey, there is no way you can skip a message. If you cannot process a message, you basically have to acknowledge it and move on to get the next message. It's up to the consumer to decide what needs to happen in case, you know, there is let's say the message is bad. Like, do you skip it? Do you put it on another topic? Do you, you know, send it over? Like, how you handle that incident, it's completely up to you. There is nothing called as like a dead letter queue or anything inbuilt in Kafka. So that sort of is an important consideration. So if I have to recap this, then for exception handling, essentially the best bet is so not supported out of box, not supported out of the box. Best bet is to so consumers have to be smart about handling you know incorrect messages. Most of the strategies involve strategy can involve in pushing the message to a different queue. Okay. Then MQ out of the box supports the ability to requeue a message. It also supports dead letter queues, and it also supports or it gives you the ability of with the virtue of, like, you know, pushing back the message on the queue, allowing you for, like, you know, basically taking a chance that some other consumer will pick it up, which can actually consume the message. Okay, so with that, we have got like about 7 minutes left. I'm going to change the order a little bit. I'm going to first show message prioritization because that I think it's super cool. The pub sub example we'll cover it in like about 30 seconds after the message prioritization, and so will we for the routing example. Now, in terms of message prioritization in Kafka, you cannot prioritize a message. Okay, so no message priority possible. In case you want to prioritize a message, you have to put it in a separate queue, in a separate topic, sorry, where you're saying that, like, you know, this is a high priority message topic, and then you have high priority consumers. So there is no way for you to essentially reorder the consumption of messages. So if you have like an unimportant message before a very important message, the unimportant message has to be, you know, read, and then only you'll get to the important message. In RabbitMQ, you have the ability of priority queues. Okay, priority queues. So in terms of priority, you're allowed to assign priority numbers from 0 to 255. It goes by configuration. Higher the number, more the priority. Okay, and let's actually look at this in an example. So MQ priority prioritization consumer. I'm just going to have one consumer in this case for this example, because that's what makes sense in order to show the ordering and everything. The second is you know, my producer. Here what we are saying is, if my message is even, okay, then it has a higher priority. If the message is not even, then it has a lower priority. So what we should see here is all the you know, what we'll see is we have produced from 0 to 19. So all the even messages will be consumed first. So as you can see, and then only once all the even messages are consumed, odd messages start consumption. Now let's say a user says that, like, hey, no, you have this rule, but in case you know, if the message is divisible by 5, then it even gets like higher priority. Okay, otherwise you keep the priority as it is. So what we are going to do is we're going to say that, like, hey, if it is divisible by 5, then give me the priority as 5. Otherwise, keep the priority intact. Okay, so let's see what that leads to. So I'm just going to clear this console for, you know, transparency. We don't need to start the consumer. This is only for the producer side change. So let's actually start the producer, and then you will see how 0, 5, 10, 15 are consumed first, and then after that all the even are consumed, and then after that all the odd except 5 and 15 are consumed. So that is fairly interesting, where you have the ability of priority queues. Let me quickly summarize the prioritization. As I'd already said, priority queues are 0 to 255. Higher the number, more the priority. Now here's the interesting thing. Because of prioritization, the order of messages actually changed. As you can see, the producer has produced messages from 0 through 19 in this order, but the consumer is consuming messages in a different order. Now that goes against Kafka's principle, where ordering in a partition is guaranteed, right? Now if you end up adding priority, so if there is priority on the messages, then what ends up happening is the ordering within a partition gets disturbed, right? Now that's sort of an important gets disturbed or violated. I think violated. That's a better word. And now that's something which goes against Kafka's contract, and that's the reason why you don't have an ability to actually prioritize the messages in a particular partition. So with that, there is a pub sub example, and just a quick overview of this is Kafka by default is pub sub, where you can have one publisher producing a messages to a topic, and you can have multiple consumers consuming from that particular topic. We already saw that n number of times during this example, during this talk. In MQ, I did not show PubSub, but PubSub is also available. And just to show you, in PubSub, basically you have this exchange mode called as fan out, where it's going to fan out, it's going to publicize all the message, it is going to distribute the message. However, one important caveat to this is the subscribers or the consumers which are attached to that particular queue, when the producer is producing messages, only those get the fan out. Okay, so if a particular consumer comes up and says that, like, hey, I want the message that you send to like those two other consumers, you basically say, sorry buddy, like tough luck, you will get all the messages going forward. So that's sort of a nuance that you need to keep in mind. So in the last minute, I'll quickly summarize. So first thing is, both of them are data transmission or transfer technologies. Okay, both of them are stable in production. They have been around for a long time. Kafka is mainly a pub sub model, where the producer and consumers are smart. Okay, the second thing is Kafka is a transaction log. Actually, that should be the first thing. So Kafka is a transaction log. In Kafka, ordering is Kafka guarantees ordering within a partition. Okay, and then last but not least, message prioritization is not possible. Is not possible. Okay, on the MQ side, MQ is a queue with a smart exchange. Okay, then MQ by default, in MQ, you have prioritization is available. In MQ, messages are lost or deleted. I would say messages are deleted more than lost. Deleted once they are consumed from the queue. So this is where, depending on your use case, if you care about like this, one producer producing and n number of consumers consuming, and having to need like historical data, etc., then Kafka is where it will shine. In a PubSub model, Kafka, I've used Kafka so many times. It's definitely ends up, giving the bang for its buck. MQ, on the other hand, is it's fairly smart about scaling. So let's say you want to scale across multiple data center dynamically. MQ gives you that ability as well. So let me add that. MQ allows dynamic scaling by adding new once you add new consumers. Once new consumers are added. With that, I know we are 2 minutes over time. Thanks a lot for everybody for sticking around. Again, my name is Nikhil Nanivadekar. My Twitter handle is @NikhilNanivade. Feel free to follow me, tweet at me, and then we can move the conversation forward. Lastly, I'll leave you with this summary, and